Hello and welcome to Sleepy Scientist. I'm glad you're here, whether you've had a long day, a busy mind, or you simply love falling asleep to the sound of science. Tonight, we're diving into the mysterious, powerful, and somewhat terrifying phenomenon of tornadoes. Now, before you start imagining the whirlwinds that tear through the plains or make their way across a distant horizon, I invite you to join me in a little mental exercise. Picture yourself standing on a warm, still evening in the kind of calm that almost seems too quiet. The wind isn't stirring, the air feels thick and heavy, and you can almost feel the silence pressing against your ears. It's in these moments right before the chaos that nature is preparing for something extraordinary. You can sense that something's about to change, but you're not sure what. Now hold that thought. In this peaceful, calm atmosphere, you may notice something strange while the air is still and the temperature feels almost perfect. There's a faint shift, just a subtle feeling that the world around you is waiting for something. You can feel the tension, like the breath before a great exhale. In the distance, a flash of lightning streaks across the sky, followed by the deep rumble of thunder. Yet there's still no wind. The air is thick, heavy with moisture, and the sky is almost too quiet. This moment of stillness is crucial in understanding tornadoes. It's the calm before the storm, and this silence can actually be a sign that something powerful is building up. How is it that a peaceful scene like this, with no obvious warning, can lead to one of the most destructive forces on Earth? Let's explore the science behind how tornadoes form. Starting with the elements at play in the atmosphere. At the core of tornado formation is the interaction between temperature, pressure, and moisture in the atmosphere. You see, tornadoes don't just spring up out of nowhere. They require very specific conditions. The first thing we need to understand is that the atmosphere is a constantly shifting, swirling mass of air. It's full of different air currents that are constantly moving at various speeds and directions. The key to tornado formation is the way these currents interact with one another. Picture the atmosphere as a giant sea with warm, moist air sitting on top of cooler, drier air, much like layers of a cake. When these air masses begin to mix, when the warm air starts rising while the cooler air sinks, you begin to see the first signs of instability. This unstable mixing of air masses is the starting point. You might wonder why this leads to something as chaotic as a tornado. The answer lies in the pressure difference created when the warm air rises. As this air rises, it creates a vacuum of lower pressure, below which draws more air in. It's like when you open a window on a hot day, the cool air rushes in to fill the space. However, it's not just this rising and sinking air that causes instability. It's also the wind patterns that contribute. Imagine you're standing on the surface of the earth, feeling the wind at your back. But the higher you go in the atmosphere, the wind begins to change direction, maybe even blowing in the opposite way. This is what we call wind shear, the difference in wind direction and speed at various altitudes. When the lower-level winds blow in one direction and the upper-level winds blow in the opposite direction, it creates a spinning motion in the atmosphere. This is where things start to get interesting. If the wind shear is strong enough, it can cause a rotating column of air to form. This column is initially horizontal, but as it continues to spin, it gets tilted by the rising warm air. The result is a rotating updraft of air called a mesocyclone that is the precursor to a tornado. So while the air around you may feel still and peaceful in those moments deep within the atmosphere, forces are already at work, pulling and twisting the air into a shape that could become dangerous. But we're not there yet. A mesocyclone is not yet a tornado. The real magic happens when this rotating column of air makes contact with the ground. Now you might be asking, how does this transition happen? It's like a tightly wound spring finally being released. The mesocyclone must meet a specific set of conditions to drop down from the cloud base and connect with the ground. When this happens, the tornado is born. To make matters more interesting, there's another critical component to tornado formation: the interaction between atmospheric instability and the presence of moisture. Tornadoes are often formed in conditions where warm, moist air from the Gulf of Mexico meets cooler, drier air from the Rocky Mountains or Canada. This clash creates an environment ripe for severe weather. The warm, moist air rises, and as it cools, it condenses, releasing latent heat. This heat release intensifies the updraft and increases the rotation of the mesocyclone. This process is like a pot of water boiling on the stove. When the heat turns up, the water starts to bubble and swirl. As the temperature difference between the air masses increases, so does the intensity of the storm. It's this intense energy transfer that fuels the tornado, providing the necessary force for the air to rotate faster and become more organized. The more intense the instability, the stronger the tornado's potential. This is why tornadoes are more common in certain regions like Tornado Alley in the United States, where warm, moist air regularly meets cooler, dry air, creating the perfect breeding ground for these violent storms. Now take a moment to imagine the atmosphere around you again. The stillness is deceptive, isn't it? In that calm, the tension is building, and the air is almost like a coiled spring. It's not just the wind or the temperature, it's the whole system working in concert, moving and shifting in response to unseen forces. Just as a quiet storm can seem like nothing more than a calm night, the conditions for a tornado are already set hidden behind the invisible layers of the atmosphere. But don't let the stillness fool you. Beneath the surface, nature is preparing for a spectacular and often dangerous release of energy. Tornadoes, like many natural phenomena, remind us that calm can sometimes be the most deceptive state of all. Nature moves in rhythms, and in those quiet moments, before the storm, you can almost feel the entire atmosphere gearing up for what comes next. So as you lie back and drift into sleep, think about that calm before the storm and the amazing forces at play that can suddenly erupt into a swirling force of nature. As you sink deeper into the world of storms, I invite you to imagine something else. This time, think of a massive sky filled with dark, swirling clouds. These clouds are no ordinary puffs of water vapor. They're enormous towers of moisture, towering thousands of feet into the air. As the warm air continues its upward journey, it encounters these towering clouds, and the storm system begins to take shape. This stage is crucial, as it's in the towering clouds, known as cumulonimbus clouds, that tornadoes truly start to form. But what makes these clouds so special? Why is it that they, more than any other type of cloud, are responsible for the formation of tornadoes? The answer lies in their size, structure, and energy. A cumulonimbus cloud, often called the thunderstorm cloud, is the result of a strong updraft of warm, moist air. This updraft is so powerful that it causes the cloud to grow vertically, sometimes to heights that extend into the stratosphere. You can think of this updraft as a sort of invisible elevator, lifting the warm air higher and higher until it reaches the colder layers of the atmosphere. As the air rises, it cools and condenses, forming water droplets that make up the cloud. Now imagine these clouds as massive engines of energy. As they grow taller, they pull in even more warm, moist air from the surface, creating a cycle of rising air that intensifies with every passing second. This process is known as convection, and it's the same principle that powers things like hot air balloons or even the formation of thunderstorms. But here's where things get really interesting. It's not just the rising warm air that causes these clouds to form. It's the interaction between the warm and cold air. and the resulting difference in pressure and temperature that creates the immense energy needed for a tornado to form. Within these towering clouds, a phenomenon called the updraft-downdraft cycle begins to take shape. The updraft, the rising column of warm, moist air, can reach speeds of up to 100 miles per hour. It's this force that fuels the growth of the cloud, and the more intense the updraft, the more powerful the storm becomes. But the process doesn't stop there. Along with the updraft, there's also a downdraft, which is the downward movement of cooler, denser air that forms at the rear of the storm. This downdraft plays a crucial role in tornado formation because it can create the wind shear, the changes in wind direction and speed that are necessary for creating a rotating updraft. In other words, the interaction between these two opposing air currents, the updraft and downdraft, creates the conditions for the rotation that forms the foundation of a tornado. But don't be fooled by their relative calm appearance from a distance. These clouds are teeming with invisible energy, twisting and turning as the winds above and below interact with each other in a delicate dance. This interaction is where the real magic happens. You might wonder, how does a seemingly innocent updraft become a full-fledged tornado? How does this once benign cloud system suddenly spiral into something so dangerous? The answer lies in the connection between wind shear moisture and the organization of the updraft. As the winds at higher altitudes blow in different directions from the winds at the surface, the updraft begins to spin in a horizontal direction. Over time, this spinning motion gets tilted by the rising air, eventually creating a rotating column of air, a mesocyclone. But why do these mesocyclones sometimes remain harmless, while others drop down to the surface, becoming full-blown tornadoes? To understand this, we need to look at the dynamics of the atmosphere once again. The moment that the mesocyclone reaches a certain intensity, when the updraft is strong enough and the wind shear is pronounced, the cloud base starts to lower and a visible funnel begins to form. This funnel of air is what we recognize as a tornado, but it's not yet finished. In fact, the process of tornado formation isn't instantaneous. It's the result of a delicate balance of pressure, wind shear, moisture, and temperature. All of these elements have to align perfectly in just the right way for the tornado to materialize. Even with all of these perfect conditions, not every mesocyclone will create a tornado. In fact, only about 25% of mesocyclones actually result in tornadoes. So when you witness the raw power of a tornado, you're looking at a rare, precise combination of factors that have come together at just the right moment. Imagine then the enormity of the forces at work in a storm like this. The rising and falling air, currents, the complex dance of pressure and temperature, and the unrelenting power of nature, all converging in a small pocket of the atmosphere. It's no wonder that tornadoes are considered one of nature's most unpredictable and awe-inspiring phenomena. And yet, even though we understand much of the science behind their formation, we're still in the early stages of fully understanding how tornadoes behave once they touch down on the Earth's surface. That, as you might guess, is where things get even more complicated. So as you drift deeper into the world of tornadoes, let's take a step back and think about the nature of the calm before the storm. You can't help but wonder, how does such a peaceful, serene moment, like the one you felt at the start of our journey, lead to the violent spinning winds of a tornado? The process is subtle, complex, and in many ways a masterpiece of nature's engineering. It's all in the way the atmosphere moves, twists, and shifts in response to forces we can't always see. Now imagine the air around you starting to hum with electricity, an unseen force crackling in the atmosphere, setting the stage for something powerful. You might notice the hair on your arms standing up, a tingling sensation you can't quite explain. It's not your imagination. It's the first sign of something truly dramatic unfolding. In this section, we'll explore the role of electrical energy in tornado formation, particularly focusing on how thunderstorms and lightning contribute to the dramatic sudden birth of a tornado. When you look up at a thunderstorm, you may see flashes of lightning streaking across the sky, illuminating the clouds' turbulent movements. But did you know that lightning is more than just an atmospheric light show? It's a vital component in the overall dynamics of tornadoes. As the storm intensifies, the growing energy within the cloud is released in the form of lightning strikes, and these bolts carry far more than just light. They are harbingers of instability, signals that the atmosphere is charged and ready to explode with forces of nature we can barely begin to fathom. So how does this connection work? As warm air rises and cool air sinks within a thunderstorm, it begins to separate into positive and negative charges. In essence, the storm begins to form its own little electric ecosystem. The warm air, which rises rapidly, carries positive charges with it, while the cooler air concentrated in the upper layers of the cloud becomes negatively charged. This charge difference sets the stage for the dramatic lightning strikes we see. But more importantly, this imbalance of energy also serves as a conduit for the forces required to bring a tornado to life. When a strong updraft continues to feed the thunderstorm, the storm's intensity grows, and the charged particles within the cloud move around more frantically. This stirring of air within the cloud, this chaotic energy, is where tornadoes take form. It's like stirring a bowl of soup, where ingredients are whirling around in a vortex. The updraft strengthens, and with it, the storm's electric charge becomes more pronounced. Think of this process as a pressure cooker slowly building steam. As the storm's energy increases, so too does the likelihood of that energy finding its way to the surface, creating a tornado. You might wonder, though, how exactly does lightning play a role in a tornado's birth? Lightning does not directly cause tornadoes, but it is deeply connected to the energetic environment that makes tornadoes possible. Lightning is a symptom of the energy running wild in the atmosphere, signaling that the forces are becoming more organized, more intense. In some cases, researchers suggest that the presence of lightning can actually help intensify the updraft within the storm. The hotter the lightning strikes, the more energy the storm gains, and the more likely it is that a tornado could spin out of the chaos. What's even more fascinating is that tornadoes and lightning often go hand in hand. A tornado is most likely to form in storms that are already producing lightning. Some scientists believe that the presence of lightning serves as a kind of precursor to tornado activity, alerting us to the presence of a rapidly intensifying storm. This connection between tornadoes and lightning isn't just an interesting quirk of nature. It is a piece of the larger puzzle that helps scientists predict when a tornado might form and where it will touch down. However, predicting the precise moment a tornado will form remains a significant challenge. Even though lightning provides a clue, the complexity of the atmosphere makes it difficult to pinpoint with accuracy when a tornado will drop from the clouds. The interaction between the storm's updraft and downdraft, the temperature differences, and the shifting wind patterns all have to line up perfectly for a tornado to form. But the presence of lightning serves as a sort of indicator that the storm is ready to release its energy. It's almost as though the storm is saying, "I'm winding up, preparing for the next big release of energy." So as you continue to imagine the storm, let's take a moment to reflect. Picture yourself standing on the ground, looking up at the storm. What do you feel the sky darkening overhead, the air becoming thick and heavy, the slight tingling on your skin as the storm builds? Lightning crackles in the distance, briefly illuminating the dark clouds. The energy is palpable. You can sense the tension in the air, the anticipation of the storm's fury. And just as the storm releases its light, you wonder, what happens next? How does this energy lead to the twisting winds of a tornado? The storm is reaching a critical point, and everything now hangs on the balance between the warm, moist air and the cooler, denser air aloft. It's at this moment that the winds begin to swirl, creating the conditions necessary for tornado formation. But even though you can feel the storm's energy building around you, the tornado itself remains elusive. It hasn't yet formed, but it could at any moment. The role of lightning then becomes more than just a flashy display. It's a signal, a beacon in the atmosphere lighting the way for the tornado's potential birth. It's a reminder of the tremendous forces at work in the storm and how they all work together to shape the most dangerous and awe-inspiring of weather phenomena. You can almost hear the thunder rumbling in the distance as you stand beneath that immense, swelling sky. The air has turned thick with tension, and the swirling winds, barely perceptible at first, are growing in intensity. The storm is building, and it's becoming clear that something extraordinary is about to happen. But how does all of this energy, lightning, wind, and rising air transform into a tornado? The answer lies in the precise alignment of atmospheric forces that, once in sync, allow a tornado to form from the swirling chaos of the thunderstorm. Let's delve deeper into the structure of a storm that produces tornadoes. At the heart of it all is a powerful feature known as a mesocyclone. Picture it as the storm's own miniature whirlpool, an enormous rotating column of air. This rotation begins with wind patterns that flow at different speeds and directions at different altitudes. When winds at the surface blow in one direction and winds higher up blow in the opposite direction, the air begins to spin horizontally. This creates a type of spin that could eventually tilt vertically as the storm continues to intensify, creating a mesocyclone. But why does this matter? This rotating column of air is the foundation of tornado formation. As the storm grows stronger and more organized, the mesocyclone becomes more pronounced, creating a supercell, an incredibly powerful type of thunderstorm that can produce tornadoes. Think of it as a whirlpool in water, but instead of liquid, it's air that's spiraling violently. The stronger the mesocyclone, the more likely it is that the storm will produce a tornado. Once the mesocyclone forms, it's like a giant invisible funnel. But for a tornado to develop, the mesocyclone needs something else: low-level wind shear. Wind shear refers to the change in wind speed and direction at different altitudes. It's this variation in winds that allows the horizontal spin within the mesocyclone to get tilted upright, eventually forming the vertical rotation we recognize as a tornado. Without sufficient wind shear, the mesocyclone remains just that: a rotating column of air that might never fully materialize into a tornado. The forces at play in the atmosphere need to be in perfect harmony. The temperature differences between warm air and cool air must also create a strong convective updraft to feed the storm's energy. It's like a dance between the warm, moist air rising from the Earth's surface and the cooler, denser air descending from the upper atmosphere. This interaction is crucial because it's what keeps the storm's energy in motion, maintaining the rotation that could eventually lead to the formation of a tornado. Imagine the storm growing more intense with each passing moment. The mesocyclone tightens and strengthens, fed by the upward force of the rising warm air. The winds, now rapidly swirling, create the perfect environment for a tornado to form. Yet despite all the necessary ingredients, a tornado still won't form until the conditions align just right. It's a delicate balance, a moment where all the atmospheric forces converge, giving birth to the twister. If even one component is slightly off, too much wind shear, not enough moisture, or an insufficient updraft, the tornado might never appear. Now imagine yourself standing there, watching the storm's energy swirling around. You can see the clouds forming darker and darker as the winds pick up. You know that the mesocyclone is there beneath all that turbulence, quietly building its power. The storm has reached a critical point. Will it release the funnel of destruction, or will it dissipate, leaving only the memory of a near miss? What's most fascinating about this process is that the tornado's formation is not always predictable. It's like watching a seed germinate. Sometimes it takes root, and sometimes it doesn't. Tornadoes don't always form just because the right conditions are present. There's a level of unpredictability that adds to their mystique and danger. And though scientists have learned a great deal about how tornadoes form, there's still a sense of mystery that surrounds the exact moment they emerge. Tornadoes are not inevitable in every thunderstorm with a mesocyclone. The dynamics of each storm are different, and even with the right conditions, not all supercells will produce tornadoes. It's a humbling reminder of how little control we have over the forces of nature. And yet, we keep watching, waiting, wondering when will the tornado drop from the sky. As the storm reaches its peak, there's a moment of calm before the tornado takes form. The winds seem to pause, the air feels heavy, and the atmosphere holds its breath. This is the calm before the storm, the brief moment in which the tornado's birth is imminent. It's as though the storm itself is waiting, collecting its final energy, before releasing it all at once in a dizzying spiral of destruction. This stillness, though unsettling, is actually a sign that the tornado is about to appear. The transition from the mesocyclone to a full-fledged tornado can be swift, with the air around you shifting in a matter of seconds. One moment you might feel the winds push and pull in different directions, and the next moment you might feel the tornado's presence, a deep rumbling that shakes the ground beneath your feet, the sound of distant thunder that seems to grow louder with each passing second. The calm is almost over. The energy that has been building for hours is ready to release, and the tornado is about to form. It's at this moment that we find ourselves at the threshold of nature's most powerful and unpredictable storm. With a swirl, a twist, and a rush of air, the tornado is born. Its path is unpredictable, its destruction terrifying, and its beauty undeniable. But it all began in the same way, quietly, with the gathering forces of wind, heat, and energy, until it became something much, much bigger than all of us. You feel the energy in the air shift once more, and the tension builds like the crescendo of a great symphony. The tornado has taken shape, and it begins to spin, picking up speed as it stretches downward from the sky. It's both a terrifying and fascinating spectacle as the whirling winds swirl and roar in a violent embrace of nature's raw power. The next question that naturally arises is what exactly happens inside the tornado? What fuels this whirlwind of destruction, and why does it behave the way it does? The tornado's structure is deceptively simple, yet its behavior can be utterly unpredictable. At the core, a tornado is just a rotating column of air. But what's fascinating is that this column of air can stretch for hundreds of meters, sometimes even miles, depending on the storm's power. Within this spiraling vortex, you'll find a mix of fast-moving winds, incredibly low pressure, and turbulence that can toss objects high into the sky like leaves in the wind. The tornado's internal structure can vary depending on its size, strength, and the conditions of the surrounding atmosphere. At the heart of the tornado is a region known as the eye, which is often calmer than the surrounding area, though not without its own eerie qualities. Imagine being inside the eye of a tornado, still yet surrounded by violent forces that are whirling around at incredible speeds. The winds near the core can reach over 300 miles per hour in the most violent tornadoes, capable of uprooting trees, demolishing buildings, and lifting entire cars off the ground. These extreme conditions make it easy to understand why tornadoes are so destructive. As you watch the tornado spin, you may notice how the intensity of the winds changes. The rotational velocity increases as the tornado narrows, and this is where the tornado's true power lies. The narrower the funnel, the faster the winds spiral inward. This narrowing can reach a point where the winds inside the tornado exceed 300 miles per hour, enough to tear apart almost anything in its path. But the fascinating part is how this acceleration occurs. The funnel is like a funnel-shaped highway for wind, with air converging from all directions at increasing speeds as it moves toward the center. But why do the winds spin so quickly? It's all a result of conservation of angular momentum, a physics principle that states that when an object, in this case air, is spun, its rotation speeds up as it moves inward. You can think of this like a figure skater pulling their arms in during a spin, causing them to spin faster. In a tornado, as the winds are drawn toward the center of the vortex, they speed up, creating the ferocious winds that we associate with these storms. Interestingly, the wind speeds in a tornado aren't constant. The tornado can have areas of strong winds right next to areas of calmer air. Some tornadoes have multiple wind cores, causing the tornado to twist and writhe like a snake. It's a chaotic, swirling mess of wind and pressure, making it difficult to predict exactly what will happen in any given tornado. One tornado may be a quick, narrow vortex with devastating winds, while another might span a larger area with slower-moving winds that cause widespread destruction over a longer period of time. As the tornado intensifies, another phenomenon can occur: the formation of debris clouds. These are the billowing masses of dirt debris and anything else that gets caught in the tornado's mighty grip. The debris cloud can stretch high into the air, sometimes obscuring the tornado itself, making it seem as if the sky itself has turned black. The debris caught in these clouds can be anything from pieces of wood and metal to entire trees and vehicles. The tornado's immense power can even lift and carry large structures, scattering them across fields like paper in the wind. But what's perhaps most remarkable is the fact that tornadoes seem to have minds of their own. They don't follow a predetermined path. There's a randomness to their behavior that makes them both fascinating and terrifying. A tornado might veer left-right or shift direction entirely in the middle of its storm. One moment, it could be heading straight for a populated area, and the next, it could change course completely, sparing lives but still leaving destruction in its wake. This randomness is a result of the dynamic nature of tornadoes. They respond to changes in wind speed, direction, and temperature. One shift in the storm's environment can cause the tornado to change its behavior. This makes predicting exactly where a tornado will go difficult, even with modern technology like Doppler radar. Meteorologists rely on patterns and past observations to make educated guesses, but ultimately, the tornado's path is largely determined by the forces of nature, wind pressure, temperature, all of which are in constant flux. While tornadoes can be incredibly destructive, their unpredictability and behavior also leave scientists in awe. Despite the ability to predict the likelihood of tornadoes forming, there's still so much about their internal dynamics that remains a mystery. The way that wind pressure and temperature work together to produce such a powerful force of nature is a reminder of just how much we still have to learn about the world around us. The most violent tornadoes, with their winds exceeding 200 mph, are known as EF4 or EF5 tornadoes. These are the tornadoes that leave a wake of devastation, tearing apart entire communities. But even the smaller tornadoes can cause significant damage. EF1 and EF2 tornadoes, while less powerful, can still uproot trees, destroy roofs, and cause significant structural damage. So whether you're witnessing the quiet formation of a weak EF0 tornado or the terrifying spectacle of an EF5, the destructive potential of these forces of nature is undeniable. What's most fascinating is how a tornado begins to dissipate. Once the storm's energy begins to wane, the tornado slowly loses its force. It's like a spinning top that gradually loses speed until eventually it comes to a stop. The air, once swirling violently, slows down. The funnel begins to stretch and widen, and the winds lose their intensity. Eventually, the tornado completely disappears, leaving behind only the aftermath of its passage, broken trees, destroyed buildings, and the lingering sense of awe and fear that follows in the wake of such an incredible force. The tornado's life cycle is short-lived, but in that brief moment, it leaves an indelible mark on the landscape. The energy that drives these storms is awe-inspiring, as is the way nature has evolved to create such powerful phenomena. But as you stand there watching the tornado dissipate and the winds slow, you are reminded once again of the incredible forces that shape the world we live in. As the tornado dissipates and the winds calm, you may find yourself reflecting on what you just witnessed, the violent, swirling forces of nature now reduced to silence. But what happens next? The storm is over, but the calm after the storm is an equally fascinating phenomenon in its own right. You may notice that the world around you seems different, now quieter, somehow as if the atmosphere is holding its breath before it releases another gust of wind. This period of calm isn't just a physical sensation, it's actually a crucial part of the storm's life cycle and one that's worth exploring. When a tornado lifts and the storm begins to weaken, the sky often turns still, and the pressure inside the storm system equalizes with the air pressure outside. This is when the mesocyclone, the rotating updraft at the heart of the storm, begins to lose its strength. The intense winds that once whipped around with such ferocity now seem to slow down. This brief moment of calm is when the atmosphere takes a deep sigh, giving everyone a chance to feel the weight of what just happened. In the aftermath of the storm, the landscape can often feel eerily silent. With the roaring winds gone, there's a stillness that feels almost unnatural. The birds, animals, and even the air itself seem to pause, as if nature is taking a moment to process the violent forces that just passed through. It's as if the energy of the storm has been sucked into the void, leaving nothing but the echoes of its passage. But is this silence truly a sign of peace, or is it simply the calm before another storm? It's important to remember that while the tornado itself has subsided, the larger storm system may still be lingering in the atmosphere. Tornadoes rarely form in isolation. They are often the result of supercell storms, which can produce other types of violent weather, like hail thunderstorms, and even more tornadoes. In fact, tornadoes are just one piece of a much larger atmospheric puzzle. As you wait for the calm to break, the question arises, why is it that these extreme weather systems tend to occur together? Supercells are massive rotating thunderstorms that can span dozens of miles. They are responsible for some of the most dangerous and destructive weather phenomena on Earth, including tornadoes. A supercell can persist for hours, feeding on the warm, moist air that rises from the ground and the cooler, drier air aloft. The combination of these two different air masses is what gives supercells their power, causing them to rotate and create the conditions necessary for tornado formation. And even after a tornado has formed and dissipated, the supercell itself can continue to produce dangerous conditions for hours. As the winds settle, you may wonder why some tornadoes appear to just vanish, leaving no trace of their passage beyond the debris scattered in their wake. The truth is, tornadoes don't always have a clean exit. While the winds may calm, the storm system itself might continue to spin, creating conditions that could spark another round of rotation. Tornadoes can spawn within these supercell storms, one after another. This phenomenon is called tornado regeneration, where a storm doesn't just release a single tornado, but rather produces multiple tornadoes over the course of its lifespan. Regeneration happens when the storm's internal dynamics shift, causing new updrafts to form and rotate. This may seem like the storm is starting over, but in reality, it's simply the complex dance of atmospheric forces, winds, temperatures, and moisture continuing to interact. Tornadoes aren't just born in a single moment. They evolve over time, shifting and transforming as the conditions change. It's during these moments of calm that we often see the power of nature's unpredictability. A tornado might dissipate, but the storm system doesn't stop. It continues to churn and move, sometimes producing more tornadoes or more severe weather. The tornado itself might be gone, but its influence lingers in the atmosphere, creating new conditions that could lead to further storms. The storm doesn't release all of its energy at once. Instead, it spreads its power over time, keeping us on edge, waiting for the next shift in the weather. The stillness following the storm also raises another question. What happens to the air in the wake of a tornado? You may have noticed that the air feels different after a tornado. Thicker, heavier, perhaps even charged with a strange electric quality. This is a result of the changes in air pressure and humidity caused by the tornado's passage. As the tornado forms, it lowers the pressure in the surrounding area, creating an imbalance in the atmosphere. After the tornado dissipates, the pressure slowly returns to normal, but it can take time for the atmosphere to fully stabilize. During this period, the air can feel dense, thick with moisture, and even slightly charged. Some meteorologists have even described this atmosphere as feeling alive. In its aftermath, a powerful reminder of the energy that once surged through the region. This electric quality is not just a sensation, it's the result of electrical charges that build up in storm clouds. Thunderstorms, including those that spawn tornadoes, generate vast amounts of electricity. This charge builds in the clouds and is released as lightning strikes, but it also influences the surrounding air. After a tornado has passed, the leftover energy from these storms can make the air feel heavier, almost as though it carries the memory of the storm with it. And so, as the tornado fades into the distance, you may feel that eerie quiet, once again accompanied by the lingering hum of the atmosphere's uneven energy. It's a reminder that while the storm may have passed, the forces that created it are still active, still alive, swirling and shifting beneath the surface. The calm is not a sign of peace, but a temporary reprieve as the atmosphere begins to stabilize and prepare for the next chapter in its ever-changing dance. In the days following a tornado, the affected area will begin the slow process of recovery, but the memory of the storm's passage will remain, as will the questions it raised. Why do tornadoes form? What drives the dynamics of these massive rotating columns of air? And how does the atmosphere continue to evolve after the tornado is gone? As you continue to reflect on the storm's aftermath, you're left with one undeniable truth. Tornadoes are a profound reminder of the immense power of nature. But while the dramatic images of funnel clouds and wind-whipped debris might captivate our attention, there's something more fundamental at play behind the scenes, the science of air pressure. Tornadoes are at their core a manifestation of how our atmosphere's pressure systems interact with one another in a dance of chaotic forces. It's this pressure system, this intricate balance between low pressure and high pressure, that makes tornado formation possible. Let's take a moment to understand what exactly we mean when we talk about pressure in meteorological terms. Imagine the air surrounding you right now, gentle and calm, pushing down on you ever so slightly. This force, The weight of the air is what we call atmospheric pressure. The Earth's atmosphere is made up of a mixture of gases, mostly nitrogen and oxygen, and the weight of these gases pressing down on everything creates pressure. The higher up you go, the less air there is, and the less pressure you experience. This is why you feel a bit lighter when you're up in a high mountain, for example, or in an airplane. Tornadoes, however, form when there is an extreme difference in pressure between two air masses. Picture this: on one side of the storm, warm, moist air rises from the ground, while cooler, dry air sits aloft. The collision of these two air masses causes a dramatic shift in the balance of pressure. When this contrast is intense enough, a rotating column of air, or mesocyclone, forms. This is the precursor to a tornado. The mesocyclone is a spin cycle of energy, with powerful winds pushing in one direction and weaker counteracting winds creating a rotating vortex. It's like a whirlpool of air, a force that spins and spins, gaining strength until it touches the ground and forms the tornado we see. But why does the air spin in the first place? The answer lies in the movement of air masses and the Coriolis effect. The Coriolis effect is a phenomenon caused by the Earth's rotation. As the Earth spins, it causes moving air and water to curve in different directions depending on which hemisphere you're in. In the northern hemisphere, this rotation causes winds to turn to the right, while in the southern hemisphere, the winds veer to the left. This curving motion of the winds is what enables the development of a rotating storm system in the first place. The Coriolis effect essentially twists the rising warm air into the rotation that can become a tornado. As this air continues to rotate, the winds begin to funnel inward, creating a vacuum at the center of the mesocyclone. This vacuum effect helps to concentrate the energy, causing the winds to increase in speed as they move inward and downward. The combination of high and low pressure spinning winds and the Coriolis effect creates the perfect environment for a tornado to form. It's a system that relies on delicate balance. Too much pressure difference, and the storm becomes uncontrollable. Too little, and the tornado doesn't form at all. This interaction of forces is not just an abstract theory. It's something we can witness in real time. Tornadoes aren't born from the air. Randomly, they are a reflection of how the atmosphere responds to the conditions around it. Every time a tornado forms, it's like watching a grand natural experiment unfold, where the balance between warm and cool, high and low pressure spins and spirals into a visible, tangible phenomenon. And as you watch that funnel cloud twisting towards the Earth, you can't help but feel the power of all those forces converging in one moment. But tornadoes aren't always predictable. While scientists have made great strides in understanding the conditions necessary for tornado formation, the process remains somewhat elusive. Tornadoes don't always follow the rules, sometimes popping up unexpectedly, even when conditions don't seem ideal. And sometimes, despite all the signs being right, a tornado just won't form. This unpredictability is part of what makes studying tornadoes so fascinating and why meteorologists continue to study them with intensity. What are the subtle, almost imperceptible signs that make the difference between a storm that spins into a deadly tornado and one that merely brings heavy winds and rain? One of the challenges in predicting tornado formation lies in the fact that tornadoes often form in supercell thunderstorms, which are themselves difficult to predict. Supercells are massive thunderstorms that have a rotating updraft or mesocyclone at their core. These storms are capable of producing extreme weather, including hail-strong winds and, of course, tornadoes. The intensity of the storm, combined with the right conditions of moisture, temperature, and wind, can lead to the formation of a tornado. But predicting exactly when and where that tornado will touch down is still beyond our reach. The atmosphere is simply too complex, and tornado formation is the product of many interacting factors. So while we may not yet have the precise formula to predict every tornado, we have learned a great deal about how they form and what conditions are most likely to cause them. And this knowledge is essential for saving lives. Meteorologists use advanced technology like Doppler radar to detect the rotation in storm systems, providing warnings when conditions are ripe for tornado formation. But even with all the technology at our disposal, tornadoes remain one of nature's most unpredictable and powerful phenomena. Tornadoes are a stark reminder of just how much we have yet to understand about the forces of nature. They are born from the very air we breathe, shaped by pressure differences, rotating winds, and the Earth's own spinning motion. Tornadoes remind us of the delicate balance between chaos and order, between life and destruction. In the calm after the storm, when the winds die down and the sky quiets, the quiet is almost deafening, because we know that what just happened is not just a storm. It is the earth flexing its muscles, reminding us that we are merely visitors in this wild, ever-changing atmosphere. There's something eerily beautiful about the moment right before a tornado forms. The stillness of the air, the unnatural calm, can feel almost too quiet, as if the atmosphere itself is holding its breath. It's known as the calm before the storm, and it's one of the most unsettlingly peaceful moments you might ever experience. You might be standing outside, feeling the air grow warmer, more humid, watching the sky shift from blue to ominous gray, and yet there's no immediate sense of danger. This calm is a deceptive stillness, a momentary peace before nature unleashes its fury. But why does this calm happen? What exactly is going on in the atmosphere that allows tornadoes to form in such a peculiar way? To answer this, let's look closely at the precursors to tornado formation. Tornadoes often form when a supercell thunderstorm reaches a certain level of instability. Supercells are thunderstorms that have a rotating updraft or mesocyclone at their center. This rotating updraft is critical because it helps organize the storm, concentrating the energy in a single spot. When the warm, moist air near the ground meets cooler, drier air aloft, a dramatic change in temperature and humidity occurs, which creates a highly unstable atmosphere. This instability is essential for the development of a tornado, and it's what sets the stage for that calm moment right before the storm. Now here's where it gets interesting. The calm before the tornado is actually a result of the storm's intense energy. In a supercell, the warm, moist air from the surface is rapidly rising into the atmosphere, creating a powerful updraft. This rising air creates a vacuum near the surface, which results in a temporary low-pressure area. As the air swirls around this low-pressure zone, it can cause the atmosphere to become still and almost motionless at ground level. This stillness is deceptive. It may feel like nothing is happening, but beneath the surface, there's a storm of energy gathering and churning. The cumulonimbus clouds that form above the supercell thunderstorm are another telltale sign of tornado formation. These towering clouds are formed as the warm air rises, carrying moisture and energy upward. The higher the cloud rises, the colder the air becomes, and eventually, the moisture in the air condenses to form the characteristic towering thunderstorm clouds. Inside these clouds, winds are moving in different directions at different altitudes. When the wind at the surface is blowing from one direction and the wind at the upper levels is blowing in the opposite direction, the result is shear, a change in wind speed and direction that helps to spin the air. This rotation in the cloud can extend downward, ultimately leading to the formation of a tornado. You may have heard the term wind shear before, but let's dig into why it's so crucial for tornado formation. Wind shear refers to the change in wind speed and direction with height. In a supercell, this wind shear is extremely strong. The air near the ground is often moving in one direction, while the air higher up moves in another direction and at different speeds. This horizontal spinning motion of the air is what can eventually become a tornado if the storm conditions are right. The tornado itself forms when this rotating column of air is stretched vertically, becoming more concentrated as it reaches the ground. Now imagine for a moment that you're watching a storm develop from a distance. You see the sky darken, the clouds swirl, and perhaps you can feel the wind pick up. You notice the stillness, almost as though the air is waiting for something. It's in these quiet moments that the storm is gathering strength. It's in this calmness that the tornado's power is about to be unleashed. There's a sense of anticipation in the air, as if you know something's coming, but you can't quite put your finger on it. That's the paradox of tornadoes, the quiet before the roar. And this calm before the storm is not just a random quirk of nature, it's essential for the formation of tornadoes. Without this shift in atmospheric pressure, without the rotation of winds at different levels of the storm, a tornado would never form. The stillness at the surface is a warning sign that nature is setting the stage for something incredible, something unpredictable. So what can we learn from this eerie calm? For one thing, it reminds us that nature is unpredictable. Its moments of beauty and terror are intertwined. The calm is just as important as the storm itself, and without it, tornadoes wouldn't be the phenomenon they are. This balance of forces, the peaceful moments before the chaos, is a reflection of the delicate dance between the atmosphere's many variables. When everything aligns perfectly, you get a tornado. The calm before a tornado also reflects a deeper truth about the way nature operates. It's not all chaos and destruction. There's a rhythm to the storm, a reason for the stillness before the fury. And that's something truly fascinating to think about. How often in life do we experience a calm moment just before a significant change or event? Perhaps nature is trying to remind us that every storm, every challenge has its quiet moments of preparation. Just like a tornado forms when the right conditions align, the same can be said for the moments in our own lives when everything suddenly changes. As you lie there imagining the moments before the storm, the stillness becomes more profound. The air, thick with moisture, hangs heavy, as if it's waiting just as you are for something to shift. The tension between the calm and the impending chaos mirrors the way we often feel in moments of great change. Tornadoes in their raw power represent that tipping point when all the pressure, energy, and anticipation finally break free. But that stillness, that's the moment before everything comes alive. Imagine the sky above you swirling in shades of gray, the air thick and humid, the wind still as if nature itself were holding its breath. The moment feels unnervingly calm, and yet you know something powerful is lurking beneath the surface. This moment, this eerie stillness before the storm, is not just a fleeting sensation. It's the result of an intricate dance between atmospheric forces, a delicate balance between warm air, cool air, and wind that creates the ideal conditions for tornado formation. But how exactly does all of this come together? What forces are at work to trigger the sudden violent twisting of air that makes a tornado so unique? As we know, tornadoes are not just random occurrences. They require the perfect conditions to form, and it all starts with the atmosphere's instability. For a tornado to form, the atmosphere must be highly unstable. That means there's a significant difference in temperature and moisture between the warm, moist air near the surface and the cool, dry air aloft. This contrast sets the stage for a powerful storm, creating the kind of instability that can cause a tornado to form. This difference in air masses is one of the most important factors in the process. When warm, moist air rises and meets cooler, drier air, above the warm air, tries to continue rising, but it can't because the cooler air acts as a barrier. The result, strong updrafts of air, which in turn can create a rotating column of air, or a mesocyclone. A mesocyclone is a rotating updraft inside the storm, a precursor to tornado formation. These updrafts are intense, powerful, and can reach speeds of over 100 miles per hour. They concentrate the storm's energy in a single spot, causing the air to spin faster and faster. But there's more to it than just updrafts. For a tornado to actually form, the mesocyclone has to be tilted in a specific direction, which allows it to draw in the rotating air from the surface and spin it into a vertical column. The key here is the wind shear, the change in wind direction and speed with height that helps tilt the mesocyclone. Without this wind shear, the mesocyclone would be too straight, too symmetrical, and wouldn't develop the necessary rotation for tornado formation. And then there's the role of the jet stream, that high-altitude band of fast-moving air that circles the Earth. The jet stream can be a key player in tornado formation as it contributes to the instability by creating strong wind shear. When the jet stream's winds interact with those at the surface, it can cause a vertical spin that encourages tornado development. It's almost as though the atmosphere itself is stirring the pot, mixing the warm, moist air with the cooler, drier air, creating the perfect environment for a storm to explode. You may wonder, how do scientists predict this precise moment? How do they know when conditions are right for a tornado to form? Well, meteorologists rely on advanced technology, things like Doppler radar to track the winds and detect rotation in the storm, and satellite imagery to monitor temperature and moisture levels at various altitudes. These tools allow them to observe the early stages of a storm's development, even predicting when and where a tornado is likely to form with surprisingly high accuracy. But as much as technology has advanced, there is still a level of unpredictability to tornadoes. They are notoriously difficult to predict in terms of exact timing and location. This is because they form from a combination of large-scale atmospheric conditions and smaller localized factors that are impossible to fully measure in real time. In fact, scientists are still working on improving tornado prediction models, trying to better understand how the different factors, everything from wind shear to moisture levels, come together to create a tornado. Now let's zoom in and think about what happens just as the tornado is about to form. When the right conditions are met, when the mesocyclone spins in just the right way, when the wind shear is perfect, when the updrafts reach their maximum potential, something remarkable happens. The rotation extends downward from the clouds, creating a funnel of rotating air that touches the ground. The air inside this funnel is moving at speeds of up to 300 miles per hour, tearing through anything in its path. It's like nature's own vacuum cleaner picking up debris and sending it spinning through the air. And though it's chaotic, there's something almost graceful about the way the air spins, as if it's performing a complex high-speed dance. At this moment, everything is in motion. The stillness of the calm before the storm is gone, replaced by an intense, violent, unstoppable force of nature. Yet even in the chaos, there's a strange beauty in the way the tornado forms, the way the forces of wind and air combine to create such power. It's as though the storm is a living entity, growing, twisting, evolving, and finally bursting forth in all its fury. For those caught in a tornado's path, it's a terrifying experience. The winds can shred buildings, uproot trees, and toss cars like toys. The force of a tornado can be so intense that it can completely level entire neighborhoods, leaving behind only debris and destruction. But even in this devastation, the tornado remains one of the most awe-inspiring forces of nature. It reminds us of the raw power of the atmosphere and the incredible forces at play in the world around us. As you picture this moment, This turning point, when a tornado goes from potential to reality, take a moment to think about what's happening on a larger scale. What does it say about the natural world, about the forces that drive weather and climate, that such powerful, violent events can form from something as simple as air? Tornadoes serve as a reminder of the complexity of the atmosphere and the delicate balance of forces that exist within it. They remind us that just as quickly as things can calm, they can also turn violent, unpredictable, and in a sense beautiful. The tornado has formed. It's here standing tall as a pillar of destruction in the sky above you. But what happens next? What happens after the funnel touches down, when it begins its erratic, twisting dance across the landscape? You may imagine chaos, a tornado, hurling debris, creating havoc. Or perhaps you picture an almost calm, methodical swaying, like a quiet but forceful waltz through the open plains. And in many ways, you're right. Tornadoes can behave unpredictably as their power grows and shifts. But there are patterns, stages, and a method to this madness, each of which gives us a glimpse into the nature of this awe-inspiring phenomenon. When a tornado begins its descent from the clouds, it isn't a guaranteed path of destruction. Tornadoes don't always remain steady on the ground. They can skip and jump. Imagine the way a stone might bounce across the surface of a pond, causing ripples with each small leap. Sometimes tornadoes will touch down, cause damage, then lift back up into the sky, only to come down again somewhere else. This happens because the tornado's updraft isn't always consistent. It can falter, causing the tornado to weaken and lift back up temporarily before gaining strength once more. Now imagine that you're watching this from the safety of your home, though we certainly hope you're not actually caught in one. You see the swirling column above you, but the ground isn't always the place where the real drama happens. The true power of a tornado comes from its rotating updraft inside the storm itself, where the massive winds create an environment where air is being sucked up at incredible speeds. It's within this updraft that the tornado's core, that terrifying spinning vortex, begins its journey. But it isn't just a simple uniform column of air. Tornadoes behave like spirals, twisting tighter as they move, gaining strength as they descend and continuing their rampage across the earth. In the heart of the storm, things can get dangerously unpredictable. Scientists have tracked tornadoes with Doppler radar, noticing that the winds within tornadoes aren't always constant. In some instances, there can be a sudden wind shift or a dramatic increase in speed, causing the tornado to suddenly intensify or weaken without warning. Tornadoes can shift their direction, veering off course sometimes with little to no indication. If you've ever seen a tornado moving across a field, you may have noticed how it seems to twist and turn as though it were alive, adapting its course based on forces too complex to predict. This unpredictability is one of the most chilling aspects of tornadoes. But what determines a tornado's path and the extent of its destruction? What makes some tornadoes utterly catastrophic, leaving behind wide swaths of damage, while others seem to appear and vanish without leaving a trace? The answer lies in the strength of the winds and the intensity of the storm. Tornadoes are ranked on the Fujita scale, ranging from F0 to F5, based on the wind speed and the damage they cause. An F0 tornado, for example, might only cause some minor damage to tree branches or signs. It might even go unnoticed by some. But an F5 tornado, that's a whole other story. With wind speeds exceeding 200 miles per hour, F5 tornadoes can level entire neighborhoods, strip trees bare, and send debris flying through the air as if it were nothing more than dust. The highest-rated tornadoes, those at the F5 level, are the ones that grab the headlines. The sheer intensity of these storms is almost beyond comprehension. Imagine standing in the center of a tornado with winds so powerful they could rip a house from its foundation. Everything in the tornado's path can be swept away, large objects like cars or trees, as well as small things like debris or even the very ground beneath the tornado's feet. The sheer power of an F5 tornado makes the world around it seem like a fragile, easily destructible illusion. But don't be fooled, most tornadoes don't reach the F5 category. The vast majority fall somewhere between F1 and F3, with winds ranging from 73 mph to 165 mph. These tornadoes are still capable of causing significant damage, but are less catastrophic than the extreme F5 storms. Tornadoes in this range can still uproot trees, throw debris, and cause significant damage to buildings, but they are often more contained in terms of the destruction they leave behind. F1 and F2 tornadoes, for example, can cause damage to roofs, siding, and trees, while F3 tornadoes can rip entire houses apart. As tornadoes progress across the land, the path of destruction is often chaotic, with debris flying in all directions. It's not just the wind that causes destruction, but the debris itself, which can travel at incredible speeds. This is where tornadoes earn their reputation as nature's wrecking balls. The winds pick up everything in their path, trees, cars, telephone poles, and hurl them through the air like projectiles. And it's not just the strength of the winds that makes tornadoes dangerous. The speed at which tornadoes can change direction and intensity makes them hard to predict, leaving little time for people to prepare. In many ways, the tornado's unpredictability makes it both mesmerizing and terrifying. Even with advances in technology, tornadoes can still catch us by surprise. Meteorologists use their best tools like Doppler radar and satellite images to track the storm's rotation and predict where it's headed, but there are still many unknowns. One minute the skies might look calm, and the next, a massive tornado might form out of nowhere, leaving devastation in its wake. But even in its chaos, the tornado is an example of the remarkable power of the atmosphere, a reminder that the world around us is in constant flux, and that there's always something new to learn about the forces that shape our planet. Now that you've witnessed a tornado in all its devastating glory, you might wonder, why do tornadoes form? What makes the winds twist and spiral with such ferocity? What exact conditions are necessary to bring about this destructive whirlwind of air? And how do meteorologists manage to predict their paths with the kind of accuracy that's vital for saving lives? These are the questions that have fascinated scientists for decades. And to understand the tornado, you first need to understand the forces that give rise to it. At the heart of tornado formation lies a dynamic interaction between warm and cold air masses, which fuels the energy that can lead to the formation of these powerful vortices. Imagine, if you will, a calm, sunny day. The sun shines warmly upon the earth, heating the ground beneath you. Warm air rises from the surface, like invisible fingers stretching upward, seeking to escape the heat below. As this air rises, it cools, and when it cools sufficiently, it begins to condense, forming clouds, thick, towering masses of water vapor. These clouds are the starting point for most storms. However, the real drama begins when another force enters the equation: cold, dense air. This cooler air, often from high-altitude regions, rushes down toward the ground, where it collides with the warm, rising air. When this clash happens, it creates a powerful boundary, a weather front. The cold air wedges beneath the warm air, pushing it upward. This creates turbulence, an unstable atmosphere that can eventually lead to the creation of thunderstorms. And if the conditions are just right, these thunderstorms can give rise to the twisted funnels that we know as tornadoes. But it's not just the collision of warm and cold air that creates a tornado. The vertical wind shear, or changes in wind speed and direction at different altitudes, also plays a critical role. Imagine a field of tall grass. If you blow wind across it at an angle, The grass will sway in different directions, twisting and turning as it moves with the wind. In the same way, wind shear can cause the air at different heights to move at different speeds. This creates a twisting motion in the atmosphere, much like the gentle whirl of a tornado before it gains momentum. For tornadoes to form a strong updraft is necessary a vertical column of rising air. This updraft is the force that lifts the warm air high into the sky, where it can eventually reach the level of a storm cloud known as the cumulonimbus cloud. The updraft is often so powerful that it can create an enormous rotating column of air, a precursor to the tornado. If the conditions are favorable, such as the right level of moisture temperature differences and wind conditions, the rotating column can intensify, stretching downward and forming the iconic tornado shape we know. But even then, tornadoes don't just appear out of thin air. There are a few more conditions that have to line up. The storm itself needs to be unstable. In other words, there must be a significant temperature difference between the surface air and the air higher in the atmosphere. The greater the difference, the more potential energy the storm has to work with. If this instability is severe enough, the storm can escalate quickly, producing what meteorologists call supercells, the massive rotating thunderstorms that give rise to the most powerful tornadoes. A supercell can generate winds so strong that they can whip around the core of the storm, forming the rotational mesocyclone that spins and potentially leads to a tornado. It's within these supercells that tornadoes are most likely to form, especially in the central United States, a region known as Tornado Alley. But this isn't to say that tornadoes can only form in one area of the world. Tornadoes can and do form in many regions of the globe, as long as the right atmospheric conditions are present. In fact, tornadoes have been recorded on every continent except Antarctica, which is a bit too cold for these violent whirlwinds. But in places like Australia, India, and parts of Africa, tornadoes are common when weather patterns align just so. Once the tornado forms the storm, itself enters a sort of cyclical phase. The tornado will often grow and shrink as it moves across the landscape. Some tornadoes will be short-lived, lasting only minutes, while others can persist for hours, grinding across the land like a hungry beast, consuming everything in its path. And throughout this process, meteorologists are constantly monitoring the atmospheric conditions, seeking clues to how the tornado will behave next. The more data they can gather about the storm's rotation, updraft, wind shear, and cloud composition, the more they can predict the tornado's path. In addition to these basic weather conditions, the topography of the land also influences tornado formation. Tornadoes are more likely to form on flat plains, where there are fewer obstructions for the wind to interact with. Hills and mountains, while still capable of generating storms, don't offer the same uninterrupted flow of warm and cold air that the flat terrain does. This means tornadoes in mountainous areas tend to be less frequent, though still possible. On the plains, however, there's nothing to slow down, the winds allowing them to build up strength and spin out of control. So what's happening on a deeper molecular level when tornadoes form? The rapid rise of warm, moist air and the drastic shift in wind speed and direction create an environment so unstable that the air begins to spin uncontrollably. The combination of vertical and horizontal wind shear forces the air into a spinning vortex, which eventually becomes the tornado. These storms act almost like giant engines, converting the heat energy from the sun into rotational energy, which is what powers the winds of the tornado itself. The complexities of tornado formation are still not fully understood, and there's a lot that scientists are still discovering. With each storm, with each new data point, we learn a little more about the forces behind these mighty whirlwinds. It's as if nature herself is offering us clues, small pieces of a puzzle that we can only hope to assemble over time. As you let your mind wander to the immense swirling power of a tornado, you might wonder how it behaves once it forms. What makes these forces of nature so destructive? Why do some tornadoes stay relatively mild, while others become unrelenting giants, capable of flattening entire communities? Tornadoes, like any living thing, have a unique personality. Their strength, their path, and their lifespan can vary dramatically, even from one minute to the next. When a tornado first touches down, it's almost as if the earth itself holds its breath. The wind whips and twists with fierce energy, while debris is sucked into the vortex, caught in an invisible dance. A tornado's power is measured in a variety of ways, but one of the most well-known is the Fujita scale, which ranks tornadoes from F0 to F5 based on the wind speeds and the damage they cause. An F0 tornado might only leave minor damage, like a few broken branches or a knocked-over trash can. But an F5 tornado, that's a whole different beast. With wind speeds upwards of 200 miles per hour, an F5 can turn entire neighborhoods to rubble in mere minutes. Yet not all tornadoes are formed equally, and their destructive potential depends heavily on the rotational speed and updraft strength. Imagine two tornadoes, both of similar size, both tearing across a field. One of them has an updraft so strong that it pulls the storm's entire energy source upward, while the other struggles to maintain its intensity. The one with the stronger updraft will maintain a more powerful rotation with stronger winds that can last longer and cover more ground. The size of a tornado's base can vary too. Some tornadoes are wide with a massive funnel that stretches across the sky like a vast funnel cloud. Others are narrow like a rope snaking their way across the land with less fanfare. However, size isn't always the determining factor when it comes to destruction. A smaller tornado with the right combination of wind speed and intensity can still cause tremendous damage, especially if it's a fast-moving storm that catches people off guard. The speed of a tornado's movement can also vary dramatically. Some tornadoes stay in place for several minutes, slowly building up more energy before racing across the land, while others might tear across the countryside at speeds exceeding 60 miles per hour. This is another reason why tornadoes can be so difficult to predict. Sometimes the best storm warnings only give people minutes to prepare. And when a tornado is moving that fast, you don't have much time to react. You might find yourself wondering, how does this twisting vortex stay suspended in the air? Tornadoes are not simply wind. They are a mixture of multiple factors that work together to form a delicate equilibrium. The tornado's base, while rotating at high speeds, is often pulled upwards by a powerful updraft of warm air from below. This updraft feeds the tornado with energy, preventing it from dissipating too soon. It's almost as if the tornado is caught in an invisible tug-of-war, constantly being pulled up and held together by forces that are still not fully understood. If this equilibrium is disturbed, if the updraft weakens, or the cold air shifts unexpectedly, the tornado can dissipate as quickly as it appeared. It's this dynamic nature of tornadoes, this mix of power and fragility, that makes them both fascinating and terrifying. Their unpredictability is what makes forecasting tornadoes so challenging. Meteorologists use sophisticated weather models to track storms, monitor wind shear, and calculate pressure changes. But despite their best efforts, tornadoes can still form suddenly without warning or change course on a dime. Even with the advanced technology we have today, the nature of these storms remains elusive, as if the tornado itself refuses to be fully understood. But in the midst of all this chaos, there's a bit of beauty too. Tornadoes form when multiple elements of nature, wind, heat, pressure, moisture, and temperature interact in a delicate balance. It's this same interaction that allows thunderstorms to grow and evolve into the dynamic forces we see in the sky. In a way, a tornado is nature's grand spectacle, a manifestation of the atmosphere's wild, untamed energy. When you look at a tornado, you're not just seeing a destructive force. You're witnessing the raw, unfiltered power of our planet's atmosphere, a system of systems that has been in motion long before human eyes ever gazed upon the first storm. But the true question remains, how do tornadoes end? This part of the tornado's life cycle is as mysterious as its birth. After the tornado forms, it will generally follow a path of destruction, picking up speed as it goes, leaving behind a trail of damage. Eventually, however, the tornado will weaken its winds, dissipating as the storm loses its energy source. Some tornadoes gradually shrink in size until they vanish into the sky, while others may lift back into the storm cloud. In either case, tornadoes usually leave behind only a brief moment of chaos before they disappear as quickly as they arrived. In the aftermath of a tornado, the sky is often clear, leaving behind a quiet that seems almost unnatural. The calm after the storm can be as eerie as the storm itself, as if the world has exhaled after holding its breath. But the work of rebuilding and understanding is just beginning. Scientists continue to study these storms, constantly refining their understanding of how they form, how they behave, and how to predict them with greater accuracy. Each new storm, each new tornado offers a new clue about the forces that shape our world. You might wonder, is it possible to prevent tornadoes? Unfortunately, the answer is no. But understanding tornado formation and behavior has led to better early warning systems and storm shelters that save lives every year. The goal isn't to stop these incredible forces of nature, but to better coexist with them, learning how to read the signs they leave behind and preparing for what's to come. Tornadoes may be an ancient mystery, their full nature still out of reach, but through science, we've learned how to track them, understand their whims, and protect ourselves when they appear. And in that knowledge, there's a strange comfort, a quiet certainty, that though we can't control the storm, we can at least be ready for it. Now imagine yourself standing outside on a warm, summer afternoon, the sky a mixture of brilliant blues and soft whites, when almost imperceptibly the world begins to change. The winds pick up swirling in gentle eddies, and the air seems to hum with an energy that you can't quite place. There's something brewing, something about to happen. For some, the first sign of trouble might be the air growing eerily still, the kind of silence that wraps itself around you like a heavy blanket. But for others, the calm before the storm can seem far more subtle, almost like nature is simply shifting its mood. You may have heard the expression, the calm before the storm, but have you ever stopped to wonder why the world seems to hold its breath before a tornado forms? This phenomenon is both mysterious and fascinating. When a tornado is about to form, the atmosphere behaves in peculiar ways. The winds may become unusually quiet with gusts that slowly shift direction as the storm's energy begins to build. This pre-storm calm is more than just an atmospheric oddity. It's a signal of what's to come, a moment when nature is gathering its forces. The calmness you feel before a tornado might be a result of wind, shear a crucial player in the formation of these wild storms. Wind shear refers to changes in wind speed and direction at different altitudes. In a tornado's case, strong winds at higher altitudes can push against slower winds at lower levels, causing the air to twist and rotate. This twisting effect can form the invisible column of a tornado. As this rotational air begins to form, it's almost as if the atmosphere is preparing itself for an explosive release of energy, creating the eerie stillness. This silence is also tied to the temperature differences in the atmosphere. In typical storm formations, cooler air sinks while warmer air rises. However, when a tornado is about to form, there's often a sharp contrast between the two. The warm air rises rapidly, while cooler air moves in from the outside, pushing up against the warm air. This is what makes the atmosphere feel so heavy and still almost like it's caught in a tug-of-war between opposing forces. And yet the calm before the storm can also be deceiving. While the sky may seem peaceful at first glance, there's a force quietly gathering strength above your head. A supercell storm. The breeding ground for most tornadoes can be deceptively beautiful, swirling clouds that change color as the sunlight hits them, turning into shades of purple, green, and black. In fact, it's this striking combination of colors and shapes that many people associate with tornado formation. But it's the subtle shifts in pressure, humidity, and temperature that are the true indicators of the storm's violent potential. Now imagine the tornado finally touching down. The calm has shattered. What seemed like a peaceful moment turns into a force of nature beyond comprehension. The landscape shifts in an instant, as homes, trees, and even the earth itself are sucked into the storm's vortex. You might ask yourself, how does such a brief, concentrated burst of energy cause so much destruction? How is it that something so small in duration can have such a lasting impact on the land? This is where the speed and intensity of a tornado's winds come into play. When a tornado begins to form, it often draws in massive amounts of air, concentrating it into a tightly wound column of spinning wind. As this air accelerates, it gains strength and speed, allowing it to lift and toss heavy objects with terrifying ease. And as the tornado continues on its path, it often gathers more fuel, picking up speed and power from the surrounding environment. The energy drawn from the earth and atmosphere is what allows tornadoes to evolve from a mild storm to an uncontrollable force. One of the most interesting aspects of tornadoes is how their intensity fluctuates. While some tornadoes stay relatively weak throughout their lifespan, others seem to undergo sudden bursts of power. These fluctuations are often tied to changes in the storm's environment. A shift in the temperature or humidity can lead to a sudden increase in rotation speed, which in turn intensifies the tornado's winds. This is why tornadoes can change so quickly, catching people off guard even when early warnings are issued. It's a reminder that much like nature itself, tornadoes are unpredictable creatures, subject to a wide range of factors that can alter their course and strength in an instant. And then there are tornadoes that seem to defy all expectations. These rare and powerful storms, sometimes called monster tornadoes, can reach speeds that are nearly impossible to measure. Their destructive power is often compared to that of a bomb blast, as buildings and vehicles are thrown into the air with violent force. The sheer intensity of these storms often leads to extensive damage, not just in the tornado's immediate path, but for miles in every direction. These monster tornadoes can travel long distances and last for extended periods, causing devastation across entire regions. Yet despite their ability to churn through the landscape, these storms are still ultimately a mystery. Too many variables come into play for anyone to predict them with absolute certainty. As you continue to imagine these storms, you might wonder how scientists are able to study tornadoes despite their unpredictability. How do they track something that can change course with little notice? Well, storm chasers, those brave souls who venture into the heart of severe weather systems, play a vital role in gathering data. Using specialized equipment like Doppler radar and weather balloons, scientists are able to track tornadoes in real time, providing vital information that helps improve forecasting and early warning systems. In fact, one of the most remarkable advancements in tornado research has been the development of dual polarization radar, which allows meteorologists to analyze not only the strength and speed of the storm, but also the type of precipitation within it. This helps scientists better understand the storm's structure, offering new clues about how tornadoes form and evolve. Through this data, we've been able to make significant progress in understanding how to predict and track tornadoes, giving us a better chance of surviving these unpredictable events. And yet, even with all the advances in technology, there are still questions that remain unanswered. For instance, what makes some tornadoes so large and devastating, while others stay small and relatively harmless? Why do some tornadoes form in an instant, while others seem to develop slowly over time? These are the types of questions that continue to drive tornado research as scientists work to unravel the mysteries of the storm. As you settle into the quiet after the storm, the calm is a reminder that tornadoes are as much a part of the natural world as the gentle winds of a spring day. Their beauty lies in their raw, untamed power, and their mystery serves as a humbling reminder of the forces that shape our planet. The storm has passed, and now all that's left is the quiet aftermath. The world once shaken by the violent winds is now eerily still. It's almost as though the earth itself needs a moment to catch its breath, just like you do after a deep sigh. If you've ever seen the wreckage left behind by a tornado, you might wonder how something so brief could cause so much devastation. The answer lies in the sheer force of nature that these storms possess. You see, tornadoes, while brief in their duration, often carry winds that can exceed 200 miles per hour. To put that into perspective, imagine the power of a race car tearing across the landscape at speeds far faster than a human can even fathom. The winds generated by tornadoes are so powerful that they can strip entire buildings to their foundations, tossing vehicles into the air like toys, and even uprooting trees that have stood for centuries. In fact, tornadoes are so intense that their winds can exert forces greater than the most powerful hurricane. The Fujita scale, which is used to classify tornadoes based on the intensity of their winds, places them in categories from F0, weakest, to F5, strongest. An F5 tornado is capable of producing winds over 300 miles per hour and can cause complete destruction of anything in its path. These storms are so powerful that even well-constructed buildings can be reduced to rubble. It's hard to imagine that such destruction can be caused by an invisible force, one that you can't even see until it's already too late. But despite the devastation, tornadoes also hold a strange beauty. There's something mesmerizing about the way they form, how the air begins to twist and churn before giving birth to a powerful vortex. Watching a tornado is like witnessing a primal force of nature, untamed, unpredictable, and awe-inspiring. And yet, these same forces that create such devastation are the same ones that give life to the weather patterns we rely on. It's a paradox tornadoes can destroy, but they are also an integral part of the atmosphere, playing a key role in how storms develop. Tornadoes in many ways act as the Earth's release valve. They are nature's way of balancing the forces within the atmosphere. The energy that accumulates in the air, the collision of warm and cool currents, and the turbulence in the sky, these factors combine to create a system that must eventually be released. In a sense, tornadoes help to regulate the environment, preventing any one area from becoming too volatile or unstable. But here's something you might not know. Tornadoes are actually more likely to occur during certain times of the year. In the spring and summer months, when warm, moist air meets cooler, dry air, the conditions for tornadoes are ideal. That's when you'll hear meteorologists talking about tornado season, the period when the atmospheric conditions are most conducive to tornado formation. And within this season, there are certain regions where tornadoes are more common, such as the area of the United States known as Tornado Alley. So why is this area so prone to tornadoes? It has to do with the unique geography of the region. Tornado Alley is positioned in a way that makes it a hotbed for tornado activity. The combination of warm, moist air from the Gulf of Mexico meeting the cooler, drier air from Canada creates a volatile mix. This is the prime environment for tornadoes to form, as these contrasting air masses provide the instability needed for powerful storms to develop. And the presence of flat plains means there's nothing to obstruct the flow of air, allowing tornadoes to form and travel with ease. It's not just geography that plays a role in tornado formation, it's also the dynamics of the atmosphere itself. Tornadoes thrive in conditions where wind shear is high, which means there is a significant change in wind direction and speed at different altitudes. This creates the rotating columns of air that eventually turn into tornadoes. These conditions are more likely to occur in certain seasons, which is why tornadoes tend to happen most frequently in the spring and early summer. But here's the real kicker. While tornadoes are most common in Tornado Alley, they can occur anywhere. In fact, tornadoes have been reported in every U.S. state, and tornado outbreaks have occurred in places as far north as Canada and as far south as Mexico. This means that while tornadoes may be more likely in certain regions, they are not limited to a single area. So as you sit quietly after the storm, taking in the peace that has returned, you might reflect on the immense power of these swirling winds. Tornadoes remind us that for all our technological advancements and understanding of the world, there are still forces in nature that we cannot control. They serve as a humbling reminder of the raw energy and unpredictability of the Earth's atmosphere. But even in the face of this destructive power, humans have found ways to adapt. Warning systems like those used in tornado-prone regions have become more advanced, allowing us to track these storms and give people a chance to seek shelter. But no matter how much we prepare, there's no denying the mystery and awe that tornadoes inspire. They are a natural reminder of the forces at work within our atmosphere, forces that we are only just beginning to understand. Tornadoes, with their violent and unpredictable nature, are both terrifying and fascinating. And as much as we may try to predict them, they remain one of nature's most compelling mysteries. It's this combination of awe and fear that makes them so captivating. It's like staring into the heart of a storm, knowing that it holds secrets you may never fully understand. And maybe that's what makes them so powerful. The storm has now passed, but the air is still heavy with the lingering tension of nature's raw power. You might be wondering, after all this talk about the science of tornadoes and the forces behind them, what happens once the tornado has dissipated? What is left behind, and how does the Earth begin to recover? The aftermath of a tornado is often as complex as the storm itself, and it can take days, weeks, or even months for a community to rebuild and restore a sense of normalcy. But even in the wake of such destruction, there is a quiet beauty in the way nature begins to heal. When you stand in the silence following a tornado, you might notice that the landscape feels different. The air smells fresher, and there's an eerie calm that makes you feel as though the world is resetting itself. This isn't just a perception, it's part of the natural cycle. Tornadoes are incredibly powerful forces, but they are also part of a larger weather system that helps maintain balance in the atmosphere. When a tornado forms, it's often a sign of a larger weather event taking place, a clash between warm, moist air and cold, dry air that creates instability in the atmosphere. This instability is part of a delicate dance, with each storm playing a role in regulating temperature and pressure across the planet. As tornadoes rip through the landscape, they are essentially helping to rearrange the air, redistributing heat and moisture in the atmosphere. The destruction they cause is a temporary upheaval, but in many ways, it is a necessary one. Without these dramatic storms, the atmosphere would become too stable, and the Earth would lose the dynamic processes that help to create new weather patterns. In the days following a tornado, the region is often left with a changed landscape. Trees are uprooted, homes are destroyed, and entire communities are displaced. But nature is resilient. As the weather begins to settle, the air clears and the earth starts to heal. It's almost as though the land is taking a deep breath, ready to start again. This recovery process isn't just limited to the physical landscape, it also involves the atmosphere itself. Tornadoes play an important role in the global circulation of air, which helps to balance temperatures and pressures across the earth. The energy released by tornadoes contributes to the overall flow of air, helping to regulate the movement of storms, winds, and temperatures around the planet. It's a natural process that's as much about restoring balance as it is about creating chaos. But even after the storm has passed and the atmosphere has calmed, there's one more fascinating aspect to consider. How do we as humans respond to tornadoes? How do we learn to live in harmony with these natural forces? The answer lies in our adaptation and the technologies we've developed to help mitigate the damage tornadoes can cause. Over the years, advances in meteorology have led to the development of early warning systems that can help predict tornadoes with greater accuracy. These systems use a combination of radar technology, satellite imagery, and atmospheric data to track storms and issue warnings when tornadoes are imminent. By providing communities with advance notice, these systems give people a chance to seek shelter and prepare for the storm. But despite these technological advancements, tornadoes remain a force to be reckoned with. In addition to early warning systems, buildings in tornado-prone regions are often designed to be more resilient. Many homes and structures in these areas are built with reinforced foundations, stronger roofs, and materials that can withstand high winds. Some communities have even constructed storm shelters, safe havens, designed specifically to protect people during the most intense moments of a tornado. But even with all of these precautions, tornadoes are still a reminder of the unpredictable and powerful forces of nature. We can't control when or where they will strike, but we can prepare and respond in ways that help minimize the damage and protect lives. It's a partnership between science technology and nature one that allows us to coexist with the storms even as we acknowledge their power. And in the quiet moments after the tornado, as you take a deep breath and absorb the stillness, you might find yourself marveling at the complexity of it all. Tornadoes, while frightening, are part of the intricate web of life on Earth, helping to maintain balance and stimulate change in the atmosphere. They are a testament to nature's ability to renew itself, even in the face of destruction. As the sky clears and the clouds begin to part, you might find yourself wondering, just like the scientists who study them, what the future holds for tornadoes and the Earth's weather patterns. Will we continue to see these storms evolve and grow in intensity? How will the changing climate impact the tornadoes of tomorrow? The answers to these questions are still unfolding, and perhaps that's part of the mystery that makes tornadoes so endlessly fascinating. For now, though, as you drift into the calm of the evening, you can rest assured that the world is slowly recovering from the storm. The Earth is resilient, and so are we. And just as the winds eventually settle, so too will your thoughts as you close your eyes and slip into sleep. If you've enjoyed this journey, I'd be quietly grateful if you'd give this video a like or tap that subscribe button for more peaceful explorations with the Sleepy Scientist. It helps more than you might imagine. And before you drift off, I'd still love to know where in the world you're listening from and what time it is there. Leave a comment if you're feeling cozy enough to share. It's always a quiet joy to see this sleepy little community ripple across time zones and continents. Good night, sweet dreams.